Okay, I'm not sure. Anyway, hi all. Yeah, my name's Scott. I'm a final year master's student here at the university, and today I'm going to be talking to you a little bit about how we detect exoplanets using our biggest, most expensive camera, the James Webb Space Telescope. Seen here, this is it. This is it as it was leaving the Earth after successfully launching, on its way to journey about 1 million kilometers away to perform science. So, as a bit of a refresher, this is our solar system, not to scale. We've known about at least 6 of these planets since the ancient Greeks or Sumerians. We discovered a few more over the last 200 years. At one point during the early 2000s, we thought there might be somewhere around 11 planets. But now we've settled on a much more reasonable 8, with 5 dwarf planets, hundreds of moons, and thousands of comets, asteroids, and other debris. But what about planets around other stars? Well, the ancient Greeks didn't know about any of those. It actually took us until 1992 to discover our first one, when these two gentlemen, Dale and Alexander, on the left and right, discovered not 1, but 2 exoplanets around a pulsar, so a neutron star that's radio bright. So these planets definitely aren't Earth-like or habitable. They discovered these 2 planets by measuring slight variations in the time it takes for these jets to sweep the Earth. And they did this with the Arecibo Observatory in Puerto Rico, a giant radio telescope, which unfortunately kind of collapsed in on itself during the pandemic, but at least we got this out of it. Interestingly, one of the planets they discovered still holds the record for the smallest exoplanet we know of, so that's quite cool. Starting in 1992, it's a bit difficult to see with the light. Starting in 1992, we steadily built up our catalogue of known exoplanets, reaching about 50 in the first 10 years, including some around regular main sequence stars like our Sun. We hit 100 in the early 2000s, and as interest in the field grew and we improved, refined our techniques and came up with some new ones, we quickly got up to 500 by sort of 2006-7ish. Skip forward a little bit and we find a lot more. We quickly hit the 1,000, 2,000, 3,000 known exoplanet milestones, and this is in no small part due to the 2 space missions Kepler and TESS, which Chris mentioned and worked on actually. So what these 2 satellites did is they looked at a lot of stars, looking for the periodic dip in brightness caused by a planet passing in front of the star and blocking out some of the light. Up to present day, Kepler has discovered over 3,000 exoplanets all by itself, which is astounding, and there are thousands more candidate planets in the data that we're still working through. And if we push to present day, we're still discovering them at breakneck speed with archival Kepler data, TESS, Gaia, and the James Webb, as well as a variety of ground-based surveys as well. But what do these planets look like? Do they look like Earth? Well, no, not really. But that's not because we don't think there are other Earths out there. We think that we should find planets like all of them in our solar system. But we just don't have the technology to find these smaller planets closer into their stars, like the Earth or Venus, Mercury, Mars. But what we do see is really interesting, because we see planets that aren't quite like anything we have in our own solar system. So we pretty regularly find planets that bridge the gap between Earth and Neptune, taking a range of characteristics between them, such as being large rocky worlds, entirely water worlds, worlds with large gas envelopes, or anywhere in between. And we rather imaginatively call them super-Earths or mini-Neptunes. And we also see planets that kind of bridge the gap between Jupiter and the Sun. These really huge planets that really have earned their right to be called gas giants. And these can begin to blur the line between what we decide as a planet and what we decide as a star. We also see an increased diversity in the architecture of these systems, where the planets actually sit. In our own solar system, we have a pretty neat layout of the terrestrial planets, the asteroid belt, gas giants, ice giants, and then more asteroids and comets and things. But we don't see that necessarily in these other systems. So here's, I didn't realize you get like a preview. You see the Sun and Mercury just about on the left. We pretty regularly find gas giants that are orbiting at 1/10 this distance. So these planets are incredibly close to their star. They're being absolutely incinerated by them, and as such, we nickname them hot Jupiters. If, in our Goldilocks zone analogy, Mercury has the porridge that's a bit too hot, then for these planets, the porridge bowl has melted and the house is on fire. We also see the same on the outskirts of these systems. So if that's Neptune, we find planets orbiting many times further out than Neptune, where if you were somehow on the moon or something of these planets, you would be hard-pressed to tell your star apart from all of the other ones in the sky, which is a bit of a scary thought. How do we detect these exoplanets around these other stars? Stars which are pretty famous for being really bright and difficult to look at. Well, if you imagine what we might see looking at a star, we wouldn't really see much around it. Everything would be washed out by how bright it is. Imagine staring at a streetlight on a dark night. You're not really going to see whatever's around it. But if you picture what you might do looking at a streetlight on a dark night, you would just instinctively block it out. You might blot it with your thumb or just put your hand out. And when you do that, you are effectively covering the light source. When we do this with stars, it's called coronography. We've done it with our own sun, and we can also apply it to other stars. And we can see more of the region around the star, which luckily for us is where planets are, or hopefully are. And it's not perfect. We still get some, well, you really can't see, some residual scattered starlight, some glow bleeding out from behind the coronagraph. But we do have ways of dealing with this that we'll get a little bit into later. But it's a lot better. That's the main thing. On average, with coronagraphy and all of our best, newest tech, we can just about directly image planets that are on order of 1 million times fainter than their host star. You can't even see it on there. I promise you there is a planet on that slide. You just can't see it. I can see it here. But for reference, that's about the same difference. You also can't see that. About the same difference as trying to look for the glow coming off of some like children's glow-in-the-dark stickers in a room with the lights on, which is pretty difficult if you didn't know the stickers were there. Or a more common analogy that comes up is looking for fireflies sort of flying around a lighthouse. But, I mean, I've never seen a firefly or a lighthouse, so that doesn't really picture well for me. To do this, we use our really expensive camera and a lot of other cameras which are equally, well, not equally, but also expensive. And, of course, I'm talking about the James Webb Space Telescope, our newest one up there, our most expensive one up there, and hopefully our best. Otherwise, why did we spend so much on it? So, to walk you through a very quick timeline from inception to launch. So in 1996, NASA launches the Next Generation Space Telescope program, seeking plans and ideas for a successor to the Hubble, which is still pretty new and pretty shiny at the time. A few years later, the program is renamed to the James Webb Space Telescope in honor of the former director of NASA during the early days of human spaceflight, so the Gemini, Mercury, Apollo missions, James Webb. Then, if we go about a decade later, we get the delivery of the first science instrument for the James Webb, and this is MIRI, the mid-infrared imager. This was built by a lot of people, but had some pretty large contributions from Cardiff and Leicester universities here in the UK. The following year, we have two more instruments. The Fine Guidance System does what it says on the tin, allows the telescope to point where it wants to, and NIRIS, the near-infrared imager, and slitless spectrograph, allowing us to perform spectrography, which is a pretty useful tool to have when you're looking at planets and trying to learn about them. And the following year, we round out the set with NIRCam, the near-infrared camera. When I say near-infrared or mid-infrared, the near-infrared is about 0.5 micron to 5 microns, and mid-infrared is 5 to about 28 microns. For reference, a human hair can be about 50 to 70 microns depending on your hair texture. But we're missing one pretty key important component of a telescope. We're missing the primary mirror. So, completed in 2016, the mirror is made of 18 hexagonal segments, which fit together nicely, made of beryllium because it's light yet strong, really useful for a space mission where you're working with a limited weight allowance and allows you more weight in your science instruments. And they're coated with a super thin layer of gold and glass for reflectivity and protection. If you happen to be some aspiring thief who wanted to step above stripping wires for copper or stealing catalytic converters for the platinum and rhodium that's inside them, if you were to scrape all the gold off the James Webb, you'd only be able to sell it for about $4,000, which isn't much. And that's obviously ignoring all the practicalities of how you would go about doing that. But now we've got all of our instruments, ingredients to make a telescope. So we begin putting it through testing. The instruments have already been going through it this entire time. We've been going through cryogenic testing. Can it survive the harsh coldness of space? Vibration testing. Can it survive a launch? And just making sure everything works as it should. And these ramp up in the lead up to launch, scheduled for 2018 from French Guiana, which is a popular ESA launch site. Of course, 2018 comes and goes, and the telescope isn't launched. It's delayed to 2020, but that's fine. These things happen. I'm sure nothing will happen around then that could possibly hinder this. Yeah, the COVID-19 pandemic impacted the James Webb, like everyone else. But that's fine. Okay, it's less fine, but it's still fine. Still 2021. Just the second half now. We're really starting to push what we call 2021. And a fun little tidbit, this delay, it's not really public knowledge, but this delay from October to December was because of an issue with the transponders on the telescope. So there were 4 of them, 4 antennae which allow us to communicate back and forth with it. 4 of them for redundancy. If one fails, we've still got 3. They were all made by the same company, somewhere in Italy, I think. And during testing, all 4 of them failed simultaneously, right before when the planned launch should have been in October. So someone had a stern talking to, and a new set of transponders was ordered and installed, causing that delay. But yeah, that should be the end of it. No, it's not. But, maybe, what, 5th time's the charm? Nearly. So, the final launch date for the James Webb had been pushed from 2018 to Christmas Day 2021, December 25th. And luckily, it stayed at that. On December 25th, the telescope successfully launched from French Guiana on top of an Ariane 5 rocket, which I've got a little tidbit to show you because who doesn't love a rocket launch? Hopefully the sound works. It's not, but I can't be bothered to fix it. So the telescope is up in there, in that fairing, with the Webb logo on it, and NASA, ESA, everyone who've worked on it. You're going to have to imagine the countdown yourself. It is in French, so rack your brains. Hopefully you know your 1 through 10, or 10 through 1 in this case, in French. Or it's a little less impactful without sound, but it still looks pretty cool. What you're really missing out on is the guy on comms actually says something of launching from Earth to the end of time itself, which is a really cool line. Makes you think, did he come up with it on the spot or workshop it? And he said that because one of the Webb's goals, other than just looking at exoplanets, is to look for incredibly high redshift galaxies peering back towards the start of the universe itself. So that's why he said that, which I promise you he did. So let's move on, hopefully. Yes. So, once the telescope launched from French Guiana, it was on a mission to the L2 Lagrange point in the Earth-Sun system. And the Lagrange points are basically, you can think of them as regions where the gravitational forces just kind of balance out. So an object can just sit there without too much effort to stay there. The L2 point is about 4 times further away than the moon. So if something goes wrong on the way there, or once it's there, we can't really do anything about it. That's in contrast to the Hubble, which obviously had some issues when it launched, which sits somewhere around here, maybe. So yeah, it's a lot further away than the Hubble, so it had to go right. And now might be a good time to mention that the Webb actually had over 300 single points of failure, where if any one of those things goes wrong, the entire mission is basically screwed. And most of these were related to the folding out of the mirrors and sun shield, because to fit into that rocket, they basically had to like origami pretzel the rocket in there and then fold it back out in space. But it did that. It did all of that successfully, which is a huge technical achievement. And a month later, it enters orbit around the L2 point. And now it began the 6-month-long process of calibrating itself, making sure the mirrors were aligned, and cooling its instruments down to near absolute zero. But once it had done all of that, it was ready to take its first image, and that it did. The first image taken by the James Webb was this. This is an ultra-deep field, which is a really long exposure of just a tiny patch of sky. And, I mean, wow, that's a great image. It's a little bit washed out on the screen. But what you can see is a distinctive 6 or 8 spike, if you've got good eyes, pattern, which is because of the shape of the mirrors. We've got a galaxy cluster in the center causing some lensing. You can see like around here and here. And basically anything that you see that has these spikes around it is a star, and anything that doesn't have these spikes is a galaxy. So there are hundreds of galaxies in this image taken on a tiny, tiny patch of sky. But aside from this looking cool, there's a reason we took this. And we took it to compare directly with one of the other space telescopes we already had up there, the Hubble. The Hubble had taken its own deep field previously, which, I mean, you should hopefully be able to see that this is the same patch of sky. We've got a different diffraction pattern because the mirrors are different shapes for the two. But you can still see the main highlights of the lensing and some of these brighter stars and quite a lot of galaxies. But the main difference is you can see a lot more with the Webb. You can see a lot more galaxies, and you can see them in a lot clearer of a way. They're a lot crisper. And this isn't to bash the Hubble. The Hubble's amazing, but the Webb's better for this. But now we've got our shiny space telescope. It works. So how do we look for exoplanets with it? So what we do is we apply the coronagraphy that we've seen earlier. We want to look at a star, blot it out, and we should just see the planets around it, right? That sounds easy enough. So that we did, and here it is. Here's the first exoplanet image with the James Webb Space Telescope. It looks pretty cool, right? No, you can't see the planet in there. I mean, there is that kind of like big, ugly thing in the way. Kind of looks a bit like a piece of popcorn or something. But what this is the residual scattered starlight I was talking about earlier. This is the light that's bleeding out from behind the coronagraph and is really messing up our observations. So that begs the question, how do we turn popcorn into planets? Well, what we do is we have two techniques to remove this noise. The first of which is angular differential imaging, or ADI, where what we do is we take our telescope and we take multiple images of our star at different angles of rolling the telescope. And what this does, this exploits the fact that this pattern is the telescope's unique response to a point of light. So to the telescope, it doesn't matter what rotation you're at, it's still just a point of light. Right? That makes sense. So the pattern should be the same, regardless of rotation angle. But that can't be the same for physical objects other than the star, such as a planet orbiting. The planet will appear to rotate throughout these images at different angles. So if we combine these images and just subtract out the things that remain static, what we should get is just the signal from a planet that appears to move between the images, which then we can de-rotate and get a clear, nice image of a planet from that. And the second technique is reference differential imaging, RDI. And RDI works on a similar basis of the telescope reacts to a point of light. So what we do is we observe our target and then we immediately shift to a different star of the same spectral type, and ideally one that we know doesn't have anything around it. And to the telescope, these 2 points of light should look identical, given its stability, because it's in space, there's no atmosphere sort of messing things up with turbulence. The only difference between these two should be a planet or a disk or something physical. So by removing the things that are the same, we can extract the signal from a planet. These methods are complementary to each other. We often perform both to try and get the most we can out of an image. They do have some pros and cons to each one, but we tend to just apply both to all of our images. And if we do that to this image, we get this. There's the planet. It was there the whole time, you just couldn't see it. But by applying these noise reduction techniques, we can actually, clear as day, find that there's our planet. The pattern around it is just a unique response based on, again, the shape of the mirrors and the instruments. But that's the planet. That's the first planet image with James Webb. This was a NeoCam filter, 3.5 microns, but we can do the same for MIRI at longer wavelengths, 11 microns. It's a different shape because it's a different instrument, but you know the highlight is there's still a planet there, regardless of what wavelength you're looking at it in. So we've proved how we can use the telescope to find exoplanets, and the longer it's up there, the better we're getting at doing it. So what have people been doing with it since it launched? This is from a really recent paper that hasn't actually come out yet, from I think a month or two ago. And what this is with MIRI now, so the mid-infrared. These are images of two white dwarfs, these black hexagon things where you can really see the shape of the mirror. And this dot here and this dot here, yeah, you can see them. They are candidate companions, planets around white dwarfs. This isn't something new. We know of a few planets around white dwarfs already, but this would be a first for the James Webb. And this thing up here is just a galaxy that happened to be in the image. So that's exciting, that's cool. What else is James Webb slated to try and do over the next year and several years? Well, one of those goals is to hunt for exomoons. Yes, we do just stick exo in front of it and it works. So we're going from detecting just the planets to the planets and the moons, which is hugely important if we're trying to figure out the habitability of these worlds, because on Earth, for example, the moon is a huge part of why life can exist and flourish. We want to characterize the atmospheres using spectroscopy and transit spectroscopy. And to do that, we have the end goal of hopefully finding biosignatures or technosignatures, so just gases or molecules in the atmosphere that are indicative of life, like phosphine on Venus, or things like the degradation of the ozone layer by us. We might see similar things on these other worlds that will give us indirect evidence for life. And of course, just finding more exoplanets and adding to that graph from the very start. The more worlds we know about, the better picture we have of just what's going on in the universe as a whole. So where next? The James Webb should stay in orbit around L2 for about 10 years before it runs out of fuel and drifts off into space, I suppose. I haven't actually thought about it too much. But there's a really exciting lineup after that, or before, sort of during that, over the next few years. So, from the ground, we've got the extremely large telescope, slated to have first light by 2030, the long-awaited sequel to the Very Large Telescope. This will be by far the world's most powerful optical telescope, and it will collect more light than all of the current 8 to 10 meter telescopes in the world, like, simultaneously. We've got the Nancy Grace Roman Space Telescope, slated to launch, I think, 2027. That's actually retrofitted from some spare American spy satellites that were donated to NASA by one of their agencies. They gave NASA two and a half telescopes, sort of on the same level or better than the Hubble, which apparently were just spares for them. They stripped out all of their spying equipment and just gave them the frame and the mirrors, and then NASA had to fill in all of the electrics and science stuff again. But that will hunt for exoplanets using gravitational lensing, which is a different method we haven't talked about, but it will discover more planets. And lastly, and furthest away, and also maybe most excitingly, the Habitable Worlds Observatory is a space telescope slated for the next few decades. And this will be an entirely dedicated observatory to hunting for worlds like the Earth. It will span the ultraviolet through to the infrared, so including optical, which is a pretty large wavelength range. We can see a lot of interesting things in that. And it has this really cool concept for an entirely detached sunshield, which would have to be launched up separately from the rocket. So it would be 2 launches to get this into space, which, I don't know, that's pretty cool to me. But, in summary, the field of exoplanets has grown exponentially since its inception in the late 80s and early 90s. We've gone from not knowing about any exoplanets to having over 5,500 of them. When I started uni, there were 4,000. And in the time it's taken me to write this talk, we've discovered like 20 more, I think. The idea that we might discover life or signs of life on another world has gone firmly from being science fiction into just being science. And with that, thank you. I will now attempt to answer any questions you might have.